Every single year, humans produce over 50 million tons of charcoal worldwide, enough to fuel barbecue grills from New York to Tokyo for decades, while providing cooking fuel for over 2 billion people who depend on charcoal for their daily meals. This ancient fuel source burns hotter than wood, produces less smoke than logs, and can be stored for years without deterioration, making it one of humanity's most reliable energy sources. But here's what's absolutely incredible. Modern charcoal production transforms ordinary wood into concentrated fuel through processes that remove over 70% of the original weight, while doubling the energy content per pound. So how do millions of trees get transformed into the uniform charcoal briquettes that power backyard cookouts and industrial applications around the world? Today, we're breaking down the extraordinary process inside one of the world's largest charcoal manufacturing facilities, where over 800 tons of raw wood gets converted into concentrated fuel every single day through controlled burning processes that have been perfected over centuries of industrial development. Make sure to subscribe as we explore the fascinating science behind creating one of humanity's oldest and most efficient energy sources. The journey begins in sustainable forestry operations that harvest hardwood trees specifically grown for charcoal production, with species like oak, hickory, and maple providing the dense wood structure that creates high-quality charcoal with superior burning characteristics. These aren't random logging operations. They're carefully managed forests where trees get harvested on rotation cycles that maintain forest health while providing consistent raw material supplies. Wood selection processes identify trees with optimal moisture content, wood density, and minimal defects that could affect charcoal quality. Modern forestry operations use portable moisture meters and density measurements to evaluate standing trees before harvesting, ensuring that only suitable wood enters the charcoal production stream while maintaining sustainable forest management practices. Transportation of harvested wood involves specialized logging trucks that can carry over 40 tons of logs while maintaining load security during transport to manufacturing facilities. These heavy-duty vehicles operate on dedicated forest roads designed to handle massive weights while minimizing environmental impact through erosion control and wildlife protection measures. At the manufacturing facility, incoming logs undergo quality inspection that verifies wood species, moisture content, and physical condition that affect charcoal production, efficiency, and final product quality. Advanced wood scanning systems can detect internal defects, decay, or foreign objects that could damage processing equipment or create safety hazards during high-temperature operations. Debarking operations remove tree bark using rotating drum systems that mechanically strip bark while preserving the underlying wood that becomes charcoal feedstock. The bark removal process uses controlled tumbling action that separates bark from wood without creating excessive wood loss or damage that would reduce production efficiency. Log cutting systems reduce whole trees into uniform lengths optimized for charcoal kiln loading and heat distribution. Precision cutting equipment creates wood pieces typically measuring between 6 and 12 feet in length, with length consistency enabling efficient kiln packing that maximizes wood utilization while ensuring uniform heat treatment throughout each production batch. Wood sizing operations further reduce logs into smaller pieces that optimize surface area exposure during charcoal production while maintaining piece sizes large enough to create marketable charcoal products. Splitting equipment creates wood pieces with consistent cross-sectional dimensions that promote uniform heat penetration during the carbonization process. Moisture management represents a critical aspect of charcoal production because wood moisture content directly affects carbonization, efficiency, energy consumption, and final charcoal quality. Wood seasoning operations reduce moisture content from typical green wood levels of 40 to 60% down to optimal levels below 20% through controlled drying processes. Air drying systems use natural atmospheric conditions, enhanced by mechanical ventilation, to remove moisture from stacked wood over periods ranging from several months to over 1 year, depending on wood species and local climate. Conditions. Advanced monitoring systems track moisture reduction progress, while weather protection prevents rain absorption that would extend drying times. Kiln drying accelerates moisture removal using heated air circulation systems that can reduce wood moisture content to target levels in days rather than months. These controlled drying operations require careful temperature management to prevent wood cracking or warping while achieving uniform moisture distribution throughout wood stacks. Storage and handling systems maintain massive inventories of seasoned wood in covered facilities that protect material from weather while enabling efficient material flow to charcoal production kilns. Automated conveyor systems and mobile equipment move wood throughout the facility while maintaining complete traceability from forest source through final charcoal product. Quality control testing verifies that seasoned wood meets specifications for moisture content, density, and freedom from contaminants that could affect charcoal production or product quality. Laboratory analysis includes calorific value testing that predicts charcoal yield and quality characteristics, while chemical analysis checks for substances that could create emissions or safety concerns. The prepared wood now moves toward the heart of charcoal production. Massive kilns and retort systems that transform solid wood into charcoal through controlled pyrolysis processes that occur at temperatures exceeding 1,000 degrees Fahrenheit in oxygen, limited environments that prevent complete combustion while driving off volatile compounds that would otherwise remain in the finished charcoal. The carbonization process begins in massive retort kilns that can hold over 100 tons of seasoned wood while creating the oxygen-limited environments essential for converting wood into charcoal without complete combustion. These industrial giants measure over 60 feet in length and 20 feet in diameter, creating controlled atmospheres where wood undergoes chemical transformation at temperatures that would incinerate the material if oxygen were present. Kiln loading operations stack seasoned wood using precise patterns that optimize heat distribution while maximizing wood density within each carbonization batch. Skilled operators arrange wood pieces to create air gaps that enable heat circulation while preventing settling that could create uneven temperature zones during the carbonization process. Loading a single kiln requires over 12 hours of careful wood placement. Ignition systems begin the carbonization process by introducing controlled amounts of combustion air that allow partial burning of wood to generate the heat energy needed for pyrolysis reactions throughout the wood mass. Advanced ignition controls gradually increase internal temperatures while monitoring oxygen levels to maintain the precise balance between heat generation and oxygen exclusion that creates optimal charcoal formation. Temperature monitoring systems track carbonization progress using dozens of sensors positioned throughout each kiln, providing real-time data that enables operators to adjust airflow, damper settings, and fuel inputs that optimize the pyrolysis process. Temperature control requires incredible precision because variations of even 50 degrees can dramatically affect charcoal yield and quality characteristics. The pyrolysis process transforms wood through a series of chemical reactions that begin around 500 degrees Fahrenheit and continue as temperatures rise to over 1,000 degrees. During this transformation, volatile compounds, including water, vapor, tar, and combustible gases, drive off from the wood, while leaving behind the carbon-rich residue that becomes charcoal. Vapor management systems capture and process the volatile compounds released during carbonization, preventing environmental emissions while recovering valuable byproducts that can be used as fuel or chemical feedstocks. Advanced condensation systems separate different vapor components, while thermal oxidation systems cleanly burn remaining gases to prevent air pollution. Gas collection networks route combustible vapors back to kiln heating systems where they provide supplemental fuel that reduces external energy requirements while maintaining optimal carbonization temperatures. This vapor recycling can provide up to 40% of the heat energy needed for carbonization while eliminating waste emissions that would otherwise require treatment. The carbonization cycle typically requires between 18 and 36 hours, depending on wood species, moisture content, and desired charcoal characteristics. Computer-controlled process management systems monitor multiple parameters while making automatic adjustments that maintain optimal conditions throughout the extended production cycle. Cooling operations gradually reduce kiln temperatures while maintaining oxygen exclusion that prevents charcoal combustion during the temperature reduction phase. Controlled cooling requires precise air management because introducing oxygen too early would cause charcoal to burn, while insufficient cooling time could result in spontaneous combustion when kilns get opened for charcoal removal. Kiln opening and charcoal removal operations use specialized equipment that can safely extract tons of hot charcoal while maintaining worker safety and preventing combustion that could destroy entire production batches. Mobile equipment with heat-resistant handling systems removes charcoal from kilns while monitoring for hot spots that could indicate incomplete carbonization or potential fire hazards. Quality assessment of raw charcoal involves visual inspection and testing that evaluates carbonization completeness, structural integrity, and freedom from defects that could affect final product performance. Experienced operators can identify optimal charcoal by appearance, sound, and physical characteristics, while laboratory testing verifies carbon content and calorific value. Screening operations separate charcoal into different size fractions using vibrating screens and mechanical classification systems that sort material according to market requirements for different end uses. Large pieces suitable for industrial applications get separated from smaller fragments that require further processing or different market channels. Crushing and sizing systems reduce oversized charcoal pieces to uniform dimensions while minimizing dust generation that would represent product loss and create handling difficulties. Controlled crushing preserves charcoal structure while achieving size consistency that enables efficient packaging and transportation operations. Dust collection and fines recovery systems capture charcoal particles created during handling and processing operations, recovering valuable material that would otherwise be wasted while maintaining clean working environments. Advanced air filtration prevents charcoal dust emissions, while cyclone separators concentrate recovered fines for specialized processing. Briquette production represents a major value-added processing option that transforms charcoal fines and irregular pieces into uniform fuel products with consistent burning characteristics. The briquetting process combines charcoal powder with binding agents under high pressure to create dense, uniform fuel blocks that burn more consistently than natural lump charcoal. Binding agents for charcoal briquettes include natural materials like starch or clay that hold compressed charcoal particles together, while maintaining clean burning characteristics without chemical additives that could affect food safety or air quality. Advanced binder systems can create briquettes that light easily while burning for extended periods. Compression molding systems apply pressures exceeding 2,000 pounds per square inch to form charcoal briquettes with consistent density and shape characteristics that optimize burning performance and packaging efficiency. High-pressure formation creates mechanical bonds between charcoal particles, while shaping briquettes into forms that stack efficiently for commercial distribution. Quality control for briquette production includes density testing, burn rate analysis, and ash content measurements that verify products meet specifications for different market applications. Automated testing systems can evaluate thousands of briquettes per hour, while statistical process control maintains consistent product quality across all production runs. The final processing stages transform raw charcoal and finished briquettes into consumer-ready products through packaging operations that protect the fuel while enabling efficient distribution to retailers and end users worldwide. Advanced packaging systems handle millions of individual briquettes per day while maintaining product integrity and preventing moisture absorption that could affect burning performance. Moisture control represents a critical aspect of charcoal packaging because even small amounts of water absorption can significantly reduce ignition characteristics and burning efficiency. Climate-controlled packaging environments maintain humidity levels below 30%, while protective packaging materials create moisture barriers that preserve charcoal quality during storage and transportation. Automated packaging lines fill bags with precise weights of charcoal or briquettes using computer-controlled weighing systems that achieve accuracy within plus or minus 2% of target weights. High-speed packaging equipment can fill and seal over 6,000 bags per hour while maintaining consistent fill weights that meet commercial specifications and regulatory requirements. Bag sealing operations use heat sealing or adhesive closure systems that create airtight seals, preventing moisture infiltration, while providing tamper-evident closures that assure consumers of product integrity. Advanced sealing equipment monitors seal quality in real time while rejecting any packages that fail to meet sealing standards. Quality control for packaged products involves statistical sampling and testing that verifies fill weights, moisture content, and package integrity meet specifications for different market channels. Laboratory testing includes burn testing that evaluates ignition characteristics, burn duration, and heat output under standardized conditions that simulate actual use scenarios. Bulk packaging operations prepare larger quantities of charcoal for industrial customers using super sacks, bulk containers, or specialized shipping systems that handle tons of material while maintaining product quality and enabling efficient handling at customer facilities. Bulk packaging requires specialized equipment that can handle charcoal without creating excessive dust or product degradation. Warehousing operations manage massive inventories of finished charcoal products in climate-controlled facilities that maintain optimal storage conditions while enabling efficient order fulfillment and shipping coordination. Automated storage systems can locate and retrieve specific product types while maintaining first-in, first-out inventory rotation that ensures product freshness. Distribution logistics coordinate transportation of finished charcoal products using specialized trucks and rail systems designed to handle combustible materials safely while meeting regulatory requirements for hazardous materials. Transportation. Load planning optimizes shipping efficiency while ensuring that products reach retailers and customers in optimal condition. Fire safety protocols throughout charcoal manufacturing and distribution require comprehensive safety management systems that prevent ignition while providing emergency response capabilities for potential fire incidents. Advanced fire suppression systems use specialized agents that can extinguish charcoal fires while minimizing product loss and facility damage. Environmental impact assessment reveals that modern charcoal production achieves remarkable efficiency through energy recovery systems that capture and utilize volatile compounds released during carbonization while minimizing emissions. Through advanced pollution control equipment, closed-loop processing recovers over 90% of the energy content in wood waste and byproducts. Sustainability programs focus on responsible forest management that maintains forest health while providing renewable raw materials for charcoal production. Certified forestry operations ensure that tree harvesting occurs at sustainable rates while protecting wildlife habitat and maintaining forest ecosystem services, including carbon sequestration and watershed protection. Carbon footprint analysis demonstrates that sustainably produced charcoal can provide net carbon benefits through forest management practices that sequester more carbon than charcoal combustion releases. Advanced forest management techniques include selective harvesting and reforestation programs that maintain forest carbon stocks while providing renewable energy resources. Waste heat recovery systems capture thermal energy from carbonization operations to generate steam for facility heating, wood drying, or electricity generation. Combined heat and power systems can achieve overall energy efficiency levels exceeding 80% while reducing facility operating costs and environmental impact. Economic impact extends far beyond individual manufacturing facilities, as charcoal production supports rural forestry communities while providing affordable cooking fuel for billions of people in developing countries. The industry directly employs hundreds of thousands of workers worldwide, while supporting additional employment in forestry, transportation, and retail distribution. Innovation continues, advancing charcoal technology through improved carbonization processes that increase yield while reducing processing time and energy consumption. Advanced kiln designs enable more precise temperature control, while automated process management systems optimize production efficiency and product consistency. Research and development efforts explore enhanced charcoal formulations that provide improved ignition characteristics, longer burn times, and reduced emissions during combustion. Future charcoal products may incorporate additives that enhance performance while maintaining natural burning characteristics that consumers expect. Quality certification programs ensure that charcoal products meet international standards for safety, performance, and environmental responsibility. Third-party testing and certification provide consumer confidence while enabling market access for products that meet stringent quality and sustainability requirements. Consumer education programs help users understand proper charcoal handling, ignition, and safety practices while promoting awareness of sustainability issues related to charcoal production and forest management. Educational initiatives focus on safe use practices while highlighting the renewable nature of responsibly produced charcoal. This remarkable manufacturing facility produces over 200,000 tons of charcoal products annually, providing cooking and heating fuel for millions of people while supporting sustainable forest management practices that maintain healthy forest ecosystems. The combination of traditional carbonization knowledge with modern manufacturing efficiency demonstrates how ancient technologies can be enhanced through engineering innovation. Global market expansion continues, driving growth in charcoal production as developing economies increase energy consumption, while developed markets discover the superior cooking performance that high-quality charcoal provides for outdoor cooking and specialty culinary applications. International trade in charcoal products supports economic development, while meeting growing demand for renewable energy sources. And there you have it, The absolutely incredible process of transforming millions of tons of sustainably harvested wood into concentrated charcoal fuel that powers cooking and heating applications around the world. The precision, sustainability, and economic impact of modern charcoal manufacturing showcases how traditional energy sources can be produced responsibly while meeting the needs of billions of people who depend on charcoal for their daily energy requirements. What other energy production processes would you like us to explore? Drop a comment below and let us know what you think. And don't forget to like, share, and subscribe to keep exploring more fascinating industrial journeys with us.